Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, it's my pleasure to introduce you Grant Schenneberg. He's visiting us from Berkeley, and he'll be talking about the strength of linear and semi-definite programs.
So thanks everyone for showing up to my talk. Talk about the strength of linear and semi-definite programs. You've all said you've heard several talks on this topic before, so I changed things around from the normal talk, and hopefully it'll help put things in context and it won't be so into the details as some of the talks. So I hope you enjoy it. The setting is we have these combinatorial optimization problems, and we know we know that you can't solve them exactly. They're NP hard in general to solve exactly. And so you might say, well, are they all the same? And people said, no, they're not all the same, because actually some of them you can approximate well and some of them you can't approximate well. And a lot of the recent work in theoretical computer science has been pinning down how well you can approximate these problems. And we've pinned this down pretty well for a large swath of these problems, but problems that look like traveling salesman problem, or problems that are 2 CSPs, which means that kind of they have local constraints and each constraint only depends on 2 variables. These we've been rather unsuccessful at pinning down the approximation factors. We do have at least non-trivial approximation algorithms for these problems, and some examples of these are the Lovasz theta function, this max cut algorithm by Gomans and Williamson, and the ARV sparses cut algorithm. So, and these kind of successful algorithms are all based on semi-definite programming. So kind of a useful technique seems to be semi-definite programming. And as we'll see kind of later, there's obvious ways to make these semi-definite programs stronger. And one of the main open questions is, do these techniques help? So can we get stronger or better approximation algorithms kind of without thinking too hard for these problems? So today I'm going to focus on one particular problem, which is vertex cover. So in vertex cover, you're given a graph, and you want to find a minimal kind of cover. So a cover is a set of vertices such that each edge is incident to at least one vertex in the cover. So you want to find a minimal size cover. And this problem is NP hard, but we can approximate it. And there's a simple 2 approximation, which I'll show soon. It's been shown to be NP hard to compute exactly, better than 1.36. This was by Linear and Semidefinite. Actually, it's unique games hard to do better than 2. And we're interested in how well can these linear programs and semi-definite programs do. Even in just like barely sub-exponential time, can we get better than a 2 approximation for these using these techniques? So to define things a little bit, the first thing, I'll kind of define what a linear program relaxation here is. So you start off with an integer program. So we encode the vertex cover problem as an integer program. So for each vertex in the graph, we're going to introduce a variable. The variable is going to be 1 if the vertex is in the cover, 0 if the vertex is not in the cover. And so we're trying to minimize over the sum of these variables, which is the number of variables in the cover. And for each edge, we add a constraint that says that the sum of the endpoints is greater than 1, which means one of them must be in the cover. So all I've done here, I haven't done anything. I've just rewritten vertex cover as an integer program. Vertex cover was NP complete, so is integer programming, so nothing's happened. But the kind of amazing thing is that if we relax this and we add more possible solutions and we say just anything between 0 and 1 is OK, now I have a linear program and I can solve it, but now I'm solving a different problem than what I set out to solve. And this notion of an integrality gap captures kind of the relation between the linear program and the integer program. So what it is it's the ratio between, in kind of the worst case, of the combinatorial optimum divided by linear programming optimum. So this ratio will be large if there's any instance where the linear programming optimum gets much better, right? Because we're relaxing it, so the minimization is going to decrease. So if it gets much better than the integer program. And So we can see here the integrality gap is actually 2, more or less. It's less than 2 by rounding. If you just solve the linear program, you get these fractional solutions, and we're just going to round the fraction to 0 or 1. And at most, the weight of the total solution can double, because 1/2 can go to 1, and that's doubling. That's the most it can do. And you notice that if the constraints were satisfied before the rounding, they're satisfied after, because if the sum of the constraints was greater than 1, one of them must be greater than 1/2. That one will round to 1, so the integer solution will also be a solution here. So you get that the integrality gap is less than 2 by roundings. And so in particular, this gives you an algorithm. And you can see it's greater than 2 also. And the way to do that is you have the complete graph. That's going to be our counterexample here. It has no small vertex cover, so the smallest vertex cover is n-1. But the linear program gives an optimum of n over 2. And the reason is that you can put 1/2 everywhere. If you put 1/2 everywhere, all these constraints are satisfied. So it claims to kind of found a vertex cover of size half the vertices, but no such vertex cover exists. And so the ratio between kind of n-1 and n over 2 is 2. So you get the integrality gap being at least 2 here. So let's just kind of review what happened here. What happened is we started off with an integer program, and you can look at the convex combinations of the valid integral solutions. And then we relaxed the program. When we relaxed it, this kind of polytope became bigger and admitted kind of bad solutions to it. Okay. Now you might object to this saying that this complete graph is kind of a obvious counterexample, and we can get rid of that pretty easily by just saying it has triangles in it. So in any triangle, at least 2 of the vertices must be in the cover. So I'm going to add another constraint that says that for any triangle in the graph, the sum of the vertices corresponding to them must be at least 2. Okay? And now the previous counterexample doesn't work, right? And the question is, well, what's the integrality gap here? And the answer is, it's still 2. You need to be more clever to find a counterexample, but it's still 2. And so then so we had the convex combination integral solutions. We relaxed it to linear solutions, and then this essentially creates a cut on these solutions that we have, making the polytope smaller. And the question is kind of, can we make these cuts enough to get it back so that to actually shrink the integrality gap? And you see, while the complete graph was removed as a counterexample, equally bad counterexamples still exist here. So let's just do it one more time, this time with semi-definite programming. Okay. So this is kind of almost doing the exact same thing with semi-definite programming. So we start off with our integer program here. I wrote it a little differently. So instead of the sum constraint, I have that the product equals 0, so at least one of them must be 1. That's all that's saying. You can rewrite it by just homogenizing it. So now I don't have any degree 1 terms. That's all I did here. So these are squared, and that doesn't actually change anything. Oh, I forgot. So I equals I squared means that xi equals xi squared means that xi is 0 or 1. Those are the only 2 solutions there. So here I add another variable that's essentially 1. So you can think of x naught as being 1. It could be -1, but it doesn't change things. So just think of it being 1. And then I take xi squared, which is the same as xi. I'm minimizing sum over this. And I replaced this constraint here by just multiplying by 1 there, which doesn't change anything. And I replaced the 1 by x naught there. So I haven't changed anything yet. I just homogenized it. But now from here we can actually relax, and we can say, well, instead of using these scalars, I'll allow any vectors. And so this is a relaxation. And now I just get this goofy looking program over here, which again is solvable in polynomial time because it's a semi-definite program. And now the question is, what's the relation between the solutions of this program, the semi-definite program, and the integral program? And it was shown by Kleinberg and Gomans in '98 that the integrality gap is still essentially 2. And they use this kind of special graph, or kind of family of graphs to do this, called these Frankel-Rodel graphs, which will come up more in the future too. But what I want to say about this is that, so if you have an integrality gap, it kind of requires three main components. One is you need the counterexample itself, which here is going to be a Frankel-Rodel graph. So the Frankel-Rodel graph is you have the vertices of the hypercube, and each vertex is connected to the points that are almost antipodal to it. So if you connect each vertex to its antipodal point in a hypercube, you get a matching, right? And a matching actually has a vertex cover of size 1/2. It's matching, okay? This graph is geometrically very similar. Instead of connecting to its antipodal point, each point is connected to points that are almost antipodal to it. And so geometrically, it looks kind of like a matching, but in fact, it's not, okay? So the next two components you need of the integrality gap, to show an integrality gap, is you need to show, one, that this graph actually, this counterexample, does not have a small vertex cover, which is what Frankel and Rodel showed, that this kind of graph where you connect things at almost antipodal points has no small vertex cover. Any vertex cover is almost the entire graph. And you also need to show a semi-definite solution to the problem that shows that kind of the semi-definite program thinks there is a good solution to this. And here what they did with these Frankel-Rodel graphs is they were able to create solutions kind of with the intuition I told you before, that geometrically this graph looks very similar to matching, even though its combinatorial behavior is far from that. So Kleinberg and Gomans created this SDP solution that satisfies this for the Frankel-Rodel graphs, which showed the integrality gap is 2. But again, you can introduce very simple kind of additional equations to it. So here we add one that says xi times xj is greater than 0, which is always true for these integral solutions. And that adds the corresponding constraint that vi.vj is greater than 0. And this, it turns out, this equation was not satisfied in the Kleinberg and Gomans solution. So kind of, if you just increase the program a little bit, it's not satisfied anymore. Cheriker showed that you could tweak it and satisfy it again. But what I'm pointing out here is there's kind of this cat and mouse game between kind of creating better cuts and then better integrality gaps and then better cuts and then better integrality gaps and then better cuts and better integrality gaps. And and so kind of the goal of this line of research is to systematize this and to try to get rid of the cat and mouse game, though perhaps it just creates it at a larger scale, and say what it means to kind of rule out large swaths of these linear and semi-definite programs. So the way we're going to do this is to think of things as distributions. So we're dealing with convex programs. So we can't help but include all convex combinations of valid integral solutions. Otherwise, we won't have a convex program. But we want to, so the kind of thought is we want to allow only these things. So only these things. So a convex combination of integral solutions can be thought of as a distribution over integral solutions, which is kind of a little strange. But so someone comes to you and says, well, I don't have one integral solution, but I have a whole bunch of them, and here's a distribution over them. Okay? And we have to allow this. And we'll see later why this is maybe a good idea, but just go with me here for a second. So a distribution is just a map from the kind of 0, 1 unit interval to 0, 1 to the n. We'll think of things in vertex covers throughout this. So I have a map of assignments to what vertices are in the cover, which vertices are outside of the cover. And I want these to be vertex covers. And I can encode this in this very inefficient way, which is kind of like a probabilistic long code, I guess. So for every function from 0, 1 to the n to 0, 1, I say what's the probability, given your distribution, of that function being satisfied. Okay? So if this function were just kind of 1 on one particular assignment and 0 the rest, you'd get kind of the non-zero functions would be the support, and you'd see the probability. So you see this actually gives you a distribution, but it gives you a lot more than that. So examples of kind of functions I could ask is like, what's the probability that xi is in the cover, vertex I is in the cover? What's the probability that vertex I is in the cover, but vertex j is not? What's the probability that there's 10 vertices in the cover, for example? And it turns out that you can, if someone gives you an encoding, so they give you kind of the probability of f for all f's, so think of this as a big vector, and they give you this vector, you can check that the vector is a valid, a probability distribution by checking that this thing holds. So the probability of f plus probability g is just the probability fng plus f or g for all combinations here. And you can check that the probability that kind of always true thing is 1, probability all false one is 0. And you can check that this function that corresponds to kind of valid vertex cover assignments is 1, or correspondingly the one that corresponds to invalid vertex cover assignments is 0. So you put 0 weight on invalid vertex cover assignments, and all the weight goes on valid ones. Okay, so my point is that these are things that you can check with a linear program. So I can encode, if I'm giving this vector, I can encode kind of a linear program. I can write a linear program that checks that you gave me a legitimate solution. And so we can simplify this a little bit. One way to simplify is we actually only need to check local constraints. So for if ij is an edge, we really only need to check that with the 0 probability, neither I nor j is in the vertex cover. That's enough. So we don't have to check this. We can just check these local constraints. The reason being, if there's any weight on an invalid vertex cover assignment, then if we have a true probability distribution, there'll be some weight on a violated constraint. Okay, so we can check that the constraints are always unviolated. And actually, so this program here is doubly exponential in size because the number of functions is doubly exponential in the number of variables. And you don't need this. You can actually restrict yourself to conjunctions of literals, but and then it's exponential, which is kind of the way that we'll want to think about these things being kind of exponential in n, not double exponential. But I think this notation is just easier. So I use this notation, but it doesn't really matter. No, I want D to be a distribution. So this is just like the probability space, and then you get an assignment.
As a weight or the opposite?
Okay, so yeah, so well, you can think of it that way. I'm just thinking of D being a random variable. But yeah. Okay, so now this is similar to what I said before. We want to minimize this expression here, which is just the expected number of variables that are in the cover. And for all functions f, we have a variable, which is supposed to be their kind of probability, and we want that to be between 0 and 1. And we expect this to hold for our variables. These things so that we have a valid assignment, and this thing here to hold. And then I just rewrote this using kind of the simplified things. So maybe for each conjunction, you have a variable that's probability between 0 and 1. And you check that kind of the probability of C is equal to the probability of C and I plus C and not I. So still have conjunctions. And the probability of not I and not J should be 0 for every edge. So I don't put any weight on things that are violated. And so this gives you a nice linear program here, right? I just wrote it in terms so you can see kind of how we get from distribution to a linear program. And now we're going to do something a little goofy that doesn't, just to complicate things a little more. We're going to create this thing that they call a moment matrix. And the rows and the columns are going to be indexed by these functions, f. And the ijth entry is going to be the probability of f and, or the fgth entry is going to be the probability of f and g. Okay? So I had this vector of all these things, and I'm going to create kind of a matrix out of it. And the what are some things about this matrix is that if we look at one row, it's kind of like everything in that, if we look at the F row, everything in that row is kind of like and F, right? It's like what's probably this and F happens, what's probably that and F happens. And so if we divide by the probability of F, assuming it's non-zero, it's kind of like conditioning on F happening, right? Because the probability of F and I divided by the probability of F is the probability of I conditioned on F. So if these rows kind of normalized, it's like conditioning on an event. And when you condition, you should also get a distribution of vertex covers, right? Because if I say this is a distribution of vertex covers, and I condition on an event, then I get another different distribution of vertex covers. And in particular, in the future, we'll condition on dictators, which are just like xi. So what's probably that xi is in the cover? Or let's condition on xi being in the cover. And also, a property of this matrix is that it's positive semi-definite. And the reason is that if you have an integral solution, then the matrix is just, if y is kind of this vector, this encoding vector we had, the matrix is just the outer product, this yty, right? Because the probability of f and g is 1 if f and g are both true and 0 if either f or g is 0. So it's just the outer product here. And then the linear combination of positive semi-definite matrices is also positive semi-definite. So, okay, so we have this moment matrix. Each row, each normalized row is like conditioning on an element, and each and it's positive semi-definite. Y here y would be it would be a row vector, but it would be like the row vector corresponding to the row 1. Okay, so now let's define some stuff. Let's do something cool. I'm going to rearrange the vectors, the order of these things in a particular way. And the way I'm going to arrange them is, so a function said to depend on a variable if it's ever the case that changing the value of that variable changes the value of the function. And a function is a k-junta if it only depends on, at most, k variables. Okay, so we're going to put the 0 juntas first. These are just the constant functions that are always 1 or always 0. And then we have the 1 juntas. And these are just dictator functions or anti-dictator functions. 1 juntas and 2 juntas and 3 juntas and so on. Okay, so now to get k rounds of Schrijver atoms, what I'm going to do is I'm going to insist that you give me this kind of truncated part of the moment matrix. So I'll require that you give me not all the probabilities, but all the probabilities for, say, up to 3 juntas.
So what looks like a single row in this matrix is actually a whole bunch of rows, right?
Yeah, exactly. Yeah, a real lot of them. Okay. So I'm going to. So if for vertex cover, for example, I'm going to minimize over these probability of the i's, the sum of the probability of i's. This is the number of vertices that are in the cover, and the kind of polytope I'm minimizing over is this is the one defined here. It's the kind of assignments that you can lift to this larger space here legally. And I'm going to minimize all those. And these are just the same constraints that we had before that we said held for the entire moment matrix. We're just going to insist that they hold on this small part here. Are people following this at all? You should ask questions at this point if you're not, because it won't get any better. Well, this is the worst of it. I should say this is the worst of it. So, but if you don't understand this, it won't get much better. And then Lasserre says that actually this matrix here is positive semi-definite. So for the same reason that the whole matrix is positive semi-definite, any submatrix will be also. Right, so given a solution, I want to lift it to this large space. So when I say that a vertex cover solution survives, what I need to do is define all the things on this kind of section of the moment matrix. And then I've showed that it survives k rounds of Schrijver atoms or k rounds of Lasserre. Okay. And actually, so I defined, there's 4 hierarchies. I defined 2 of them now. The other 2 are very similar to each other. And they actually use this little box here, this much smaller box. They just look at kind of 0 juntas and 1 juntas. And so the Lovasz-Schrijver, so you have some linear program. So Lovasz-Schrijver is linear. You start with a linear program, and you say x belongs to the kind of the lifting of this linear program if there's a protection matrix. So this is just the moment matrix for all the 1 juntas. So I define kind of what's the probability. Remember we said we could look at these rows as kind of conditioning on something. So you can say what's the probability. This is the probability of kind of like xi being in it. This is probability of xi and x1, xi and x2, this row here. So I give the moment matrix for this. And it turns out that the kind of consistency constraints now reduce to simply checking that the matrix is symmetric and that the first row and the first column and the diagonal are the same. And these are just all the consistency constraints that there are. The row is just conditioning on and if you condition on an event, so the ith row, and you renormalize that, this should still belong to the initial cone. So what it is saying is that if I condition on that I is in the vertex cover, I should still get a distribution that looks like a distribution of vertex covers, right? And so this is LS here. And if we want to do it, we just do it iteratively. So we iterate it. So if we want to do the rth level, we insist that each row belongs to the r minus 1th level. Okay, and so the way to kind of think of this is that you give a protection matrix, and then some adversary says but what about this row here? Show that this row belongs to the r minus 1th, and so then you take that row, you normalize it, and you give a protection matrix for that, and so on and so forth. So he can condition on the ith variable and say, show me what happens when the ith variable is in the cover. And then you give another protection matrix. It says, okay, show me now what happens when I condition additionally that the jth vertex is not in the cover. So now I've conditioned that I is in the cover and j is not in the cover. Okay, and I need a new protection matrix. And so this kind of is similar to what happens before, right, where I have the juntas. I can condition on more than one thing happening at once here, right? I can condition that I is in the cover and j is not in the cover, whereas here in LS, I can condition that I is in the cover and j is in the cover, and I can give a protection matrix that depends on the order in which these variables were conditioned on. So I can give you a different matrix if you first condition that j is not in the cover and I is in the cover. Okay, and this means that Lovasz-Schrijver is weaker than Schrijver-Adams. And additionally, you can include a positive semi-definite constraint here, and this gives you LS plus, and in the same way. Do people understand that a little bit? Okay. So a way to make it a little more concrete is this Prover-Adversary game. So the prover says I have this valid vertex cover solution that gives these weights. And here's a little adversary, and he says, well, show me what happens when I condition on this vertex here. And so the prover has to give two distributions of what happens when it's not in the cover and when it is in the cover. So here it's not in the cover, here it's in the cover. This happens probability 2/3, 1/3, and you can see if you kind of multiply these weights by 2/3, those weights by 1/3, you get those weights up there. And then the next round, the adversary says, okay, tell me what happens when this vertex is in the cover and not in the cover. And you say, well, if it's not in the cover, the graph has to look like this. That's kind of all there is to do. If it is in the cover, I'm stuck, right? There's nothing I can do. And so I don't survive 2 rounds of LS here. Of course, this is kind of a caricature of it. You need these protection matrices, but this is more or less what's going on, just to make it more concrete. And so the adversary says, ha, I gotcha. Okay. So kind of review, we have these hierarchy of hierarchies. There's 4 hierarchies that we saw. There's the Schrijver-Adams and Lasserre. These ones this is like the semi-definite constraint here. And so Lasserre is strictly stronger than Schrijver-Adams because it has a semi-definite constraint. LS plus is strictly stronger than LS because it has a semi-definite constraint. And we saw before that the LS ones kind of proceed, and Lovasz-Schrijver proceeds in these rounds, which means that I can change my distributions depending on what order things are conditioned in. So it makes it kind of easier to fool them. And so the LS is weaker than Chirali-Adams, just as LS plus is weaker than Lasserre. So this is kind of, and so we'll see some gaps for all those guys. Okay, these hierarchies all have certain things in common. They systematically add more constraints. After R rounds, you've added kind of all the valid constraints on any subset of R variables. You've actually added much more, but you've at least got this. And this shows that it's tight after n rounds, because you had all valid constraints on all variables. You're tight. And it also runs in time n to the order R. So this means that if we show a lower bound against algorithms that run for log n rounds, we've ruled out all quasi-polynomial algorithms based on these ideas here. And if you rule out all up to order n rounds, you've ruled out all sub-exponential time algorithms. Okay. And super constant, you've ruled out all polynomial algorithms. So these capture interesting algorithms in very low rounds. So one round captures, one round LS plus captures Lovasz theta function for the independent set problem. You can also use it for vertex cover. And the Goldman-Williamson relaxation of max cut. And 3 rounds of LS plus captures the ARV sparsest cut. So kind of the best that we have fall very low in these hierarchies. So they seem to capture things that people care about. Okay, so I want to talk a little bit about different results, and kind of in the proof. So these hierarchy systems can be thought of as proof systems, and so what you need in this result, you need I said you need a counterexample, and then you have to have a proof that the counterexample has no combinatorial solution, and a proof that this kind of proof system fails at seeing that. So you actually need one of the kind of themes is you need a stronger proof system to prove than these things to prove that the combinatorial example has no small vertex cover, right? Because this fails to see that it has no small vertex cover. So you need a stronger kind of proof to show that. And an interesting kind of way of thinking with these results is what kind of techniques are they using, what kind of graphs are they using, what techniques are they using on these graphs to show that no small vertex cover exists, to kind of outsmart these proof systems. Okay? And so in the first 2 examples we saw, I said use this Frankel-Rudel graph, which is this kind of, the proof is this kind of messy combinatorial proof that kind of when you change things just slightly geometrically, they change radically in the vertex cover case. The next result I'll talk about very briefly is by Aurora, Balabas, Lovasz, and Hierarchies in 2002. And I think that this was the first paper that really showed what you could do with these things and showed that you could produce pretty robust lower bounds. And they showed that the integrality gap of 2 remains even after log n rounds of Lovasz-Schrijver. So there's no polynomial time algorithm that's going to fit in the Lovasz-Schrijver hierarchy. And what they used was a random graph of large girth. So next, I'll talk very briefly about this result of mine and Luca Trevisan and Maduro Tulsiani that extends this result to order n rounds. So I think this surprised people a bit, saying that these linear programs, a large class of linear programs, actually can't solve vertex cover to approximation factor better than 2 in sub-exponential time. And not only can't do that, it can't do it on random graphs. So kind of random graphs are enough to fool linear programs. And maybe this is interesting because random graphs can't fool semi-definite programs. Right? The Lovasz theta function, which falls in the first round of LS plus, is not fooled by random graphs. It kind of sees this graph is random. You know, it looks at its eigenvalues and it says there's no way this thing has a small vertex cover. But they fool very deep into the LS hierarchy. So I'm going to go over this proof for just a little bit, just show you one particular part of it. So the graph we're going to use as a counterexample for this Lasserre is a random graph, and we're going to modify it a little bit. You don't have to, but so that it has large girth. So you just have to remove a few edges of a random graph, and you get a graph with large girth. That means there's no small cycle in it. And what that means is that any subgraph, if you pick a point and you look locally around it, it looks like a tree, right? And also a property that's used in this is that small subgraphs are sparse. So if you look at any induced subgraph that contains only a small fraction of the vertices, then that subgraph doesn't have many cycles. It has just a few more. It has just a few more edges than it has vertices, so it can't have many cycles. So it's almost a tree. It's just a little more complicated than a tree. Also, random graphs do not have small vertex covers. At least.
Regular graph or GNP?
Just GNP.
With what p?
Let's see. I'm thinking it's constant, but I don't remember. Like the expected number of vertices would be constant, but I don't really recall. Yeah, I can tell you later, but I'll have to look it up. I mean, you need enough so that this doesn't hold, right? And then you can show that the solution of putting weight kind of just over 1/2 on every vertex survives many, many rounds. And this gives you the integrality gap of 2 because almost all the vertices are required to be in the vertex cover, but the linear programming solution says that only half of them are. Yeah. And so I'll show you how to survive one round of this. And this is different than the result before, the Aurora, Lovasz, and Hierarchies, because they did things very implicitly with kind of duals of linear programs, and we did things explicitly. So go back to that model of the adversary kind of pointing at vertices and you conditioning on them. So the adversary points at some vertex in the graph, and you have to condition on that vertex being in the cover, and you have to say what happens when the vertex is in the cover and when it's not in the cover. And what we're going to want is we're going to want to only change an area in kind of a small ball around that vertex, in a constant sized ball around that vertex. And the way we're going to do it is this. In that constant sized ball, it looks like a tree, and we're going to imagine this process being run on the tree. The process is this. If your parent is 0, then you're 1 with probability 1. And if your parent is 1, then most of the time you're 0, but some of the time you're 1. So this is like noisy transmission of data down a tree. Okay? And these values are picked so that if you're 1 with probability 1/2 plus epsilon, then your child is 1 with probability 1/2 plus epsilon. Okay.
Again, just to recap, how high, I mean, what's the depth of these trees? I'm just trying to get
it's constant.
Constant depth?
Yeah.
The degree of each vertex is about?
This is the question I failed that you've all asked earlier. Say constant for now, but it won't matter. Yeah.
So this is a very sparse random graph.
Yeah, you need it. It's just dense enough that it has no small vertex covers. That's what you need. You need to put enough edges so that you get this combinatorial proof that there's no small vertex cover it goes via just a normal kind of Chernoff boundary argument.
So the fact that the girth is logarithmic has nothing to do with the fact that it's random. It's just
no.
No. Well, the degree is constant. So you need to.
You need to remove a few edges to make the girth large. But you can show that you remove square root n edges and the girth gets large. Okay. So on this part of the graph, this little circle that we cut out, this is actually a distribution of vertex covers, right? I mean, trees have small vertex covers, right? You can always cover them with 1/2. And in particular, this is a distribution of vertex covers that includes about 1/2 plus epsilon of the vertices. And so because I gave a true distribution, if I condition on this, I know what happens. It's just what happens in this distribution. So when I condition on it, if this is in the cover, then the second row, these are very unlikely to be in the cover. These are very likely to be in the cover. But as I go down further and further, this epsilon bit of noise that I add at each level adds up. And if you get a constant number of rounds, I get very, very close to the levels kind of being the same and everything being 1/2 plus epsilon again, right? Because it's this noisy transmission. So what do I do then? Within this circle of the graph, I give this distribution, which is a distribution of vertex covers, so it's definitely allowed. Outside, I leave everything 1/2 plus epsilon. And across, because the edges across, the one inside is about 1/2 plus epsilon, the one outside is about 1/2 plus epsilon, the requirement is that the sum be greater than 1. It's always greater than 1. I survive on that boundary too. But it turns out that this kind of crossing the edge and throwing it away, while it works in LS, gives you trouble later in other models, and I'll talk about that later. So I'm not going to have time to talk more about this, except to say that this shows you that you can survive one round with this kind of splash with local modification. As long as the splashes are far apart, I can always locally modify the part of the graph I care about and condition on another vertex and survive another round. And it's kind of tricky, but if the splashes get close together, you can actually use a trick to kind of fix all the vertices that are involved and make the new splashes far apart. And it turns out you can kind of survive this game for quite a while. Okay. Right. So that's all I want to say about this LS thing on vertex cover. The next couple results are these, and these are kind of interesting. They all use different instances, and I'll talk about each of them very briefly. So the first result is this. This was Feige and Ofek, and what Feige and Ofek did is they said, let's try to refute a 3-sat formula. And the way we're going to try to refute a 3-sat formula is we're going to use the standard reduction. We're going to make it into, I think the next slide I have here. So use the standard reduction, and we're going to make it into an independent set problem. And then we're going to run the Lovasz theta function on the independent set problem. And we're going to see what kind of random 3-sat formulas we can refute. And there's a standard reduction called FGLSS, and you replace each 3-sat clause is replaced by one of these gadgets here. Actually, I did it for 3XOR. So we'll do 3XOR, so you have XOR clauses. So x1 plus x2 plus x3 equals 1. So you produce it by this little gadget, this for clique. And so here x1 is kind of 0, x2 is 0, and x3 is 1. And these are the 4 satisfying assignments here. So you create one of these cliques for each clause, and then you connect the edges that contradict each other. So for example, here this one says x3 is 1. This one says x3 is 0. So there's a line between them. They should be connected. And then you can show that if the solution is satisfiable, then there's an independent set of size 1/4 of the graph. Because I just include the ones that the vertices that correspond to the satisfying solution. And if it's not, no such thing exists. So then if I can show, if the theta function can show that no satisfying assignment or no independent set of size 1/4 of the graph exists, then I can refute the 3-sat formula. And actually show that this works kind of as well as the other kind of good techniques to refute 3-sat formulas, but no better. Okay. Let's see. Okay, so that's what they're doing, but implicitly what they did is they actually gave a 7⁶ minus epsilon integrality gap for vertex cover by reducing from these 3XOR. And in this paper by, again, Madura, Luca, and I, we showed that actually you can amplify this to survive order n rounds of LS plus for the same integrality gap. So this shows that kind of, no sub-exponential linear programming algorithm is going to, exactly compute vertex cover. And within LS, these reductions don't work very well, and so you have to kind of reprove everything. So we kind of, the proof, there's a proof that LS plus doesn't work for 3 XOR by Alekhnovich, Aurora, Tralakis, and we kind of took that and combined it with a Figo effect to get this result here. The next result here I'll briefly talk about is a result by, GMPT, Georgiou, Agum, Patasi, and Tralakis. And they showed that actually on this same Frankel-Rodel graph, you can survive a super constant number of rounds of LS plus, and you get an integrality of 2 minus epsilon. Now, I told you that before I would say something about the errors and what happens to these errors and why they're kind of hard to deal with. So the semi-definite constraints that you get from LS plus, they introduce a kind of global constraint. You can't just modify things locally anymore. If you modify a little bit of something, you have to modify something else to make the program positive semi-definite. And so the way we did it is we showed that kind of actually with these 3 XOR instances, you can just modify things locally. And because you're not so close to the gap, this error dies very soon, and there's no error. In this paper here, what they did is they showed that you get these ripples, and they go throughout the entire graph. And what you can do is after each round, you just kind of round down to where the lowest ripple is. And because of the monotonicity of the constraints, you can always round down without punishing yourself, but you survive a lot fewer rounds when you do that. And the next result, which I think you guys saw, which by Cherek or Makarichev, they show it for Shirali atoms, the 2 minus epsilon. They also use a random graph. And they reduce the noise by using this really clever way that I guess that uses a trick from metric embeddings to kind of show that the noise doesn't matter. Again, you lose something in the number of rounds, it's n to the epsilon, but you gain because you don't have to, the Shirali atoms, right, you can't switch the order. The order can't matter for you, so it's a much stronger constraint. And they were able to survive to show that these stronger constraints don't work.
Get this straight. About the 7.6, so proving anything that says that it takes, if you replace this omega of n by anything that's constant, that's just implied by the hardness result, right? Just because it's 1.3 something.
Oh, right, yeah.
So,
right, so that's a...
So the Fage result is actually immediately, the stronger result is implied just by the hardness.
Well, okay, so that's a really good question. And the answer is that that's true if you assume that P does not equal NP, right? So, and if you assume that, right, yeah. So, and if you assume that there's no sub-exponential algorithm for NP hard problems, then this result is also implied, right? So it depends how strong of assumptions you want to make about NP. So kind of one neat thing about these things is that they're unconditional. The other neat thing is that you get this stratification of, sub-exponential or quasi-polynomial or whatever. But yeah, that's a great point. Okay, so the last result that I'll, I guess I'm a little low on time. So I'll just mention is that actually I was able to strengthen this result, which deals with LS plus for Lasserre. And this is the first integrality gap for Lasserre hierarchy, so that's the strongest of the hierarchies. And it survives actually order n rounds and gets you this 7.6 minus epsilon. And the kind of neat thing about it is that it comes from a proof that XOR in a random XOR formula can't be refuted by Lasserre. So let me just say, so the theorem is that a random XOR instance is not refuted even by a linear number of rounds of Lasserre. And so the proof is that a random 3 XOR formula can't be refuted by with W resolution. And this was shown by Ben-Sasson and Vigerson. And then I was able to show that actually if it has no with W resolution, the Lasserre is kind of no stronger than with W resolution. Now, the other side of it, how do you prove that a random 3 XOR formula is unsatisfiable, comes from just Chernoff type arguments, and it seems that it's odd that you can like the other one is odd that you can fool semi-definite programs using random things, but kind of the reason seems to be is that you're using random hypergraphs instead of random actual graphs, and the semi-definite programs don't pick these up very well. Okay, so yeah, you guys missed out on a beautiful proof. I'm sorry. But another neat thing about Lasserre is that reductions actually work quite well in Lasserre. And so the corollary of the result in 3 XOR is actually you get this integrality gap for vertex cover immediately from it. And it's not like LS plus where you had to kind of reprove things a little bit. The end of the story for today on this is Mutter-Tulsiani actually showed that you could take these vectors from local constraint satisfaction problems and push them through the de Noort-Saffer reduction that showed the NP hardness result and actually get the same integrality gap result. Because the size of the program, the size of the graph instance increases, you only get it for n to the epsilon rounds, which means that actually on this slide there's 5 incomparable best integrality gaps. So I think it's kind of, and still lots of room for improvement. So kind of from a higher level, SDP hierarchies, why do we care about them? Well, they're related to approximation algorithms, and some of these problems are toy problems, like vertex cover maybe, but some are problems people care about, like sparseness cut. They provide unconditional lower bounds, so we don't have to wait for people to prove that P does not equal NP to show that our techniques are feeble. They're related to proof complexity in kind of fun ways, and kind of, you're trying to come up with kind of things that fool, these hierarchies, and kind of more imaginative ways to prove that there's no solution. They're also related to local global trade-offs. If you look at like Shirali-Adams, it defines local distribution. So it's kind of saying locally everything looks good, but globally things are amiss. So this goes to a long kind of mathematic tradition of looking at local global trade-offs, and one is looking at something locally tell you something about the global structure of it. And that's definitely present here. And the last thing is average case hardness, maybe not as it's traditionally meant, but you can look and see when the integrality gap is large, like for which instances it's large. So here, in a lot of these results, we're able to show that kind of for a random instance, the integrality gap is large. Or you might be able to, sometimes you can show that for like a suitably dense instance, it's not large. So we can actually solve dense instance as well, or things like that. So you can start breaking down kind of the NP hardness results by saying on this subset we can actually do something substantial. That's all I want to say about NP hardness results. I'll talk to some of you later. So I've done other recent work. Should I end now as told about 50 minutes, or should I go on for a little longer? Or okay. So I'll just make it a little longer. So other work, we proved a new yet another proof of the XOR lemma with Thomas Holenstein, and it's kind of fun because it's really simple and easy, and it has applications to taking combining cryptographic protocols and rerunning like a weak bit commitment protocol several times and strengthening it. Also work on online algorithms for non-monotone submodular maximization. Can't hardly read all those words. But the kind of idea there is like, so you have the hiring problem or the secretary problem, where you want to pick the largest element of a set. And now instead of picking the largest element of a set, you're trying to hire, I don't know, like postdocs, and they all have different strengths and weaknesses, but you don't get any reward if their strengths overlap. You only count them once, right? We already have an expert in blah blah blah. We don't need another one. So now your maximization, your function is submodular. It's kind of a set cover problem, and you can only hire 3. And so you hire them kind of sequentially. Once you let one go, you can't hire the next one, and so you want to maximize that. I did work on property testing with Reed-Solomon codes, and I'll talk very briefly about arriving at consensus in social networks with Elchran-Mosel, and then this is older work, but Nash equilibrium concisely represented games. So you have a game, and it's not all the payoffs aren't written out explicitly. Maybe it's computed by circuit. Maybe it's a graphical game. Maybe it's another funky kind of game called an action graph game, which kind of captures local dependencies. And you want to solve questions related to Nash equilibrium, and there's kind of hardness results there. So I'll talk, just briefly kind of mention this work on arriving at consensus on social networks. So the story is there's a group of kids, and they want to go to a movie. And these are two movie theaters from my hometown. You have the Warren Old Town and the Warren East Side, and they need to pick which movie theater to go to, but they don't all know each other, and maybe they'll bump together in the hallways, and they want to pick between these otherwise indistinguishable things, but it's very important that everyone goes to the same one. Otherwise, no one's going to have any fun. And the question we look at are, what are the kind of computational issues to doing this? So assuming no game theoretic problems, these people are clever and can run any algorithm they want. Are there any inherent kind of computational boundaries to this? It was motivated by some experimental work where they basically they put people in front of a computer, and you could maybe see what color your neighbor chose, and you're trying to reach a consensus, or you're trying to color a graph, so choose something opposite them, and so there's kind of a series of works here which I won't go into anymore, but so they're kind of interesting, and they're definitely fun reads if you want some fun in your life. So this is the model very briefly. You have a weighted network. There's a network with 5 people. So I gave this to ICS. I was in China. That's my brother. He's a professor too. Everyone has a state of their own, and each edge is equipped with a Poisson clock, and the rate of the Poisson clock is equal to the weight of the edge. So when an edge rings, when the Poisson clock rings, then it's like the two people are talking to each other, right? So they talk to each other, they maybe flip some random coins, and they update their states based on the coin tosses in the previous states. And the other important thing is that this update function has to treat the two kind of choices, the consensus, the same, right? So a lot of times in distributed computing, the way that you compute consensus is to compute like the OR of things. That's not allowed here because that doesn't treat them the same. So there's no difference between the two theaters except that it really matters which one we go to, but otherwise they're indistinguishable. And so within this kind of, and also, we often parameterize it by the size of the state. So if they have 1 bit for a state, or 2 bits for a state, or log n bits for a state, what can they do? And the problems we study are coordination. So they all want to arrive at the same solution. So there's some special state, red or blue, and they need to all arrive at red or all arrive at blue. Majority coordination, which is simply computing the majority of some original signal they're given. And it's kind of interesting that one of the important kind of definitions or parameters for this problem is what we call the broadcast time. And I think this differs a little bit from some of the distributed computing stuff because of this. So the broadcast time is the time for a message to flood the network. So kind of if I start sending out something really outrageous so that everyone will send it, how long does it take for that message to reach the entire network? And this, because we use these Poisson clocks, which are kind of goofy, it seems to depend on maybe it behaves more like the expansion than the diameter. And that if there's many paths for a message to reach somewhere, it'll actually get there much faster than it will if there's just one short path. And actually, it turns out this broadcast time is the right, like you can do consensus with a constant number of bits in the broadcast time. So I don't want to go over too much, but just briefly some results. So with 1 bit, you can do it in kind of slowly and n squared time, but you can do it, this coordination. But actually, in constant number of bits, you can compute it in the broadcast time, which is maybe as fast as you'd expect to be able to compute it. And I won't show you any of this stuff. Boy, you guys are missing out here. All right. The majority coordination, it turns out, is impossible to do with 1 bit, but it's kind of fun. You can actually do it with 2 bits. And again, it's kind of more mixing time. It's this slow, like n cubed stuff. But you can actually do it with not many more bits. You need to kind of remember a neighbor, essentially. But if you can remember a neighbor, then you can do it in time of the based on the diameter, not the broadcast time, but the diameter, and plus some log n factors. Right.
What's the assumption on the geometry?
Right. So there's no assumption on the geometry here, but a lot of times, so this n cubed this is like a worst case. So it'll be much faster on most graphs than n cubed, you would think.
Can you say something on specific interesting families of graphs?
No. So this is kind of the first shot of doing this, and probably it makes more sense to get the model working better before spending too much time on the math for specific graphs. But some cases would be interesting to look at. You're right. I mean, a lot of times, with the coordination, kind of the broadcast time seems to capture a large bit of the geometry of a graph, right? Like how long it takes a message to get from one side of the network to the other. It says something about the way the network is made up. If there's one link between them, you got to wait for that one guy to go off. It's likely to take a lot longer than if it's well connected. All right. Kind of, I just want to mention, this work it's kind of in its infancy, right? It's just we proposed this kind of fun model and showed some stuff on it. And the future of this is kind of, I think it'll be interesting that you can try to make the model fit the experimental results better and what people did. Actually, you can try to modify the experimental results to fit the model a little bit better. And what I mean by that is that a lot of the experiments, everyone just had 1 bit, and they were communicating with 1 bit. And we showed that actually the strategies that we show that converge quick, some of them are very natural, but require more than 1 bit of communication. So you couldn't employ these in these networks. And so maybe they're not very good models of the way people interact. And so the experiments could be tweaked. A big thing is there's several big things. One is evolvability. How do the agents learn what algorithms to run? We just say you run this weird algorithm, go, right? And this doesn't seem to be very realistic, and could be improved upon a lot. Putting game theory in it. Maybe I don't care about. I only care if my friends are there, not the friends of their friends. Maybe I'll cheat and run a different model if it's better for me. And also, we used bounded rationality by bounding the memory of these. It's a first hack at things, but of course, a 2-bit finite state machine doesn't exactly replicate a human, and there's many ways that can fail. So there, what are other ways that we can try to do that better? Yeah, and also just to go beyond consensus, because consensus is the easiest thing you can think of. It's great because as you add an edge in the graph, the problem doesn't change. The problem consensus is always the same to reach consensus, whereas with coloring problems, it does. So you have 2 moving targets, it makes it a lot harder. But so there's lots of work in the future in this area, and if you all want to talk about it today in the interviews, I'd be happy to discuss it with you. So that's all I wanted to say. Thanks.
Okay, no questions. Thank you.
Thank you all.